So ArcKnot, what is it, and how can we use it, and why? Well, first, let's take it down a dimension. We're going from two great talks of three-dimensional folding. We're going back down to 2D, but we're expanding in a different direction, and that's the ensemble. What's the ensemble? Well, when an RNA molecule folds, it can fold many ways. And the standard that you see that you get out of a folding program is what's called the minimum free energy shape. And that's the one that particular model predicts will have the lowest energy and hence be most likely to fold. But in fact, if you take any given sequence and ask a model for suboptimal foldings, it can say, well, it could fold this way too, or this way, and give you many other possibilities that have a slightly different energy. And that means they're slightly less likely to form. But if you have thousands of these molecules, you will actually get maybe mostly these, but some of these and some of these and so forth all the way down. And for each drop of one in the energy level, it's roughly 5 times less likely to appear. But, you know, given that this is 6.3 and this is minus 5.4, it's only one apart. So that means there's about one of these for every 5 of these. So it's still going to be there. And if you don't take that into account, especially depending upon the nature of the complex of the ensemble that you have, you can end up with not getting what you expect. So that's why the ensemble is important. Now, why does it happen? Well, it happens in a way because bases have a possibility of pairing with many other bases. And the one that is the minimum free energy is just the one that has the lowest energy. But there could be other pairings. And there's something called the base pairing probabilities matrix, which once again, a lot of energy models can give you, that says, okay, this particular base pairing represented by, let's see, the 5th last one in the string, which is a C, against the first one in the string, which is a G, has a 38%, but there's also a 12% chance of it pairing differently here, and a 34% chance of it pairing differently there. So there's many possibilities. If you take that data and then fold it into presentation mode to show you, then you can get a better idea of what's going on in the ensemble. In some ways, this base pairing is both a causal factor of what you see in the ensemble, and in other ways, it's kind of a shadow. You're seeing this different base pairing because these many different forms fold in the shapes. So why would you use ArcKnot or ArcPlot? Well, primarily, the reason that I'm going to talk about most here is using it to give visibility to the ensemble. But it has other things as well. Designing using just the MFE minimum free energy shape ignores the ensemble and can lead to strange consequences. The ensemble, as presented by the DOTplot or base pairing probabilities, gives hints as to potential misfolds, which can lower the scores. And it also gives hints to design instability from those same possible misfolds, or what is sometimes called a dirty dot plot. If you've got a lot of off-axis or off your minimum free energy form, then there's more instability in the design. But that kind of off the MFE can be important for pseudoknots and for switching. When you're looking to design a switch or looking to design a pseudoknot, you want to look for hints of both forms. ArcPlot can also do other things such as pad, mutate, help you review, prune, and submit when you're working in the lab model, or you can also use it in the puzzle mode as well. And you can use metrics. The ArcPlot and ArcKnot can compute some metrics on the designs. And there's a facility called like in the configuration that allows you to do a semi-automated design review. So you can weed out some of the designs that are less likely to succeed. You can also use it to create custom dot plots for documents and so on, and many other things. I won't get into everything that it can do. As Jill mentioned, it's kind of a Swiss Army knife. but we won't go into all the features, just the main blades today. So ArcKnot is a single state in-game pop-up booster. That means that when you're playing the game, you can go down to the lightning menu here, and if you've added it to your list of favorite boosters, you can pop it up and get something that looks like this, with a bunch of controls at the top and a plotting window beneath it. The ArcKnot booster works for single state and pseudoknot puzzles, and it works in both the puzzle and lab tools. And there's thousands of different plots that you can generate, but don't worry, you don't need to know how to do all of those. There are some standard built-in ones that you can use as well. You can use it to mutate design sequences, to evaluate and review, as I said before. If you're doing a lab like this one, where you're looking for pseudoknots, and you want to snip it out of possible cases you found in natural RNA, then it will automatically pad the designs and add unique barcodes, and then allow you to do bulk submissions that way. So padding, by what I mean by padding, if the sequence that you found is shorter than the entire span that you have to use, it'll put in some static loops that help to minimize the misfolds, and I'll show a little bit more about that later. What does ArcKnot use to accomplish this? Well, it uses the in-game API of the Eterna game tool, and it uses that to compute both the MFE, the minimum free energy shape, and the base pairing probability matrix. And then it uses HTML5 for canvas for display, and it works with many energy models that are built into Eterna. ArcPlot, on the other hand, is an older version of the code line, and it supports two-state switches. So here you can see something regarding state 1 on the top and state 2 on the bottom. And so if you're designing a switch in some of the switch labs, then it's important to be able to see not just how it might form in one shape, but also how it forms in the other state. It doesn't have quite as many features. It relies on a constrained base pairing probabilities, which I currently compute offline, but I could potentially put into, excuse me, ArcKnot if we start doing switches again to have it as a booster. It might need some API hooks for constrained BPP, or I could compute it as I do offline, which is to basically, I compute a huge list of the suboptimal foldings and then do my own computation of this constrained base pairing from that. If you're interested in ArcPlot, which I won't talk about too much today for doing two-state designing, that is packaged as a public GitHub repo, and you can PM me in-game for access to that. So how do we show this ensemble data? Well, ArcKnot shows things differently than the Eterna game. On the left here, you see a standard 2D representation of a puzzle that's been solved as one particular sequence. And on the right, you see two different renderings of that same information. Here, the base pairing between the G and the U is shown by putting those two bases close together. In the arc form, it's shown by drawing a line, an arc between the two. And in the dot or DOTplot form, it's shown by having on the XY grid a dot where those two rows and columns intersect. And many people are familiar with the dot mode, fewer with the arc mode. So ArcKnot can also show pairing in two other modes. One is in grid mode. It makes it a little bit more explicit. If you're getting a design that's got a lot of pairing, then it's kind of hard to see where exactly, what does that pair up with, and grid mode makes that a little more explicit. And then there's ring mode, which instead of drawing the bases in a line, it draws them in a ring. And so it gives you a little more visibility. When you get a longer sequence, the dots and the bases are bigger. The challenge with it is that if you'll notice on the left here, we've got an area above the line, but there's also one below the line. And so we can actually draw two plots at once. and versus with a ring, there's only room for one plot. So what about pairing probabilities? Well, it draws a line between two things that pair, and by changing the color or the grayscale of that line, we can show a difference in strength of the possible pairing. So here we can see this same information or the same sequence, but now we're showing the full base pairing probabilities, which has been binned into 4 different colors. You can see that a little bit better on the dot side than the arc side. But the lighter colors, the lighter gray, is something that is less probable, and the darker is greater probability. I also, in drawing the arcs, draw the more probable arcs a little bit darker so that they're a little easier to see, and they're drawn on top. So you can also use colors. If there's only about 4 different levels of grayscale that show up well in most browsers, but you can see more colors. And so if you prefer, you can actually use a color scale to do this. And there's a way in the configuration mode of ArcPlot or ArcKnot to change what colors you use and what the color mapping is. You can also change the binning level. So there's a standard built-in, each gradation in shading is approximately equal to a 1 change in the free energy, or a roughly 5-fold decrease in probability. So the darkest would be from 0 to 20% probability, and then from 20 to 4% and so on. But you can change the binning threshold. So if you want to see a different gradation, you can do that as well. So as I said before, there are thousands of possibilities of what you can do with the plotting. And that's because in each quadrant, you can draw 78 different combinations. You can show base pairing threshold, base pairing data that's been thresholded, or the full base pair data, which I call dot for Dotplot, or none, and overlay that with 0, 1, or 2 different shapes. And there are 5 different shapes that are possible. And so all in all, there are 26 combinations of shape possibilities, 3 combinations of the grayscale or color map data, and 78 together. Put 78 in the upper and lower, have 3 modes of arc, dot, and grid, which can take 78 in each corner, and you get lots of possibilities. In addition to that, as I mentioned, you can change the binning number and size, the grayscale color map, and the threshold value. So there are literally millions of different combinations. But don't worry, you don't have to know all that. You can just use these 3 buttons up here, natural states and dot plots, to get some meaningful default plots. The not mode and simple mode is whether you're looking for pseudoknots or not. And yeah, so you can fly it quite easily. Talking more about what are the shapes that are being used. There are 2 kinds of target shapes. The TGT target is what is the empty shape that's given by the lab puzzle. And that, for things like the existing pseudoknot labs, has a large region that doesn't have any particular shape at all. But you can also, within Eterna, do a paste target structure, and that will allow you to say, I really think this shape should fold this way, and that's the user target mode, and you can see that in the bottom half. So here we've seen the target selected on the top and the user target selected on the bottom, and this plot is comparing the 2. Then there's the minimum free energy shape, which is in the given current energy model being used in the lab tool. How is Eterna predicting this particular shape is going to most likely fold? And that here is shown in purple on the top. And that's because I've selected both target and minimum free energy. Things that are common to both are shown in brown. Things that would be target only would be in blue. Well, there's nothing there, but things that are minimum free energy are shown in purple. And so the minimum free energy shape actually includes these lab tails and this portion here. And this versus the user target that was assigned to this is this shape prediction. So we can see there's a difference between what EternaFold ThresKnot is predicting on the top and what was registered in the literature for this particular shape and entered into the lab. And then there's something called the simple threshold knot. This is something that is computed, a knot shape computed inside of ArcKnot by the booster itself. And it uses the base pairing probabilities data computed by the current model. And then it applies its own threshold strategy to try and form a knot. Basically, it rank orders the base pairs in the base pairing probability and says, okay, what's the top of the list? These two bases are most likely to pair together. Then it goes down one and says, okay, what's the next one that's likely to form, and the next and the next. And if it comes across a base pair where one of the bases is already involved in another pairing, it throws that away because it says that's likely a conflict. But if it comes across a base pair that can cross over, for example, here, this base pair can cross over this base pair, then it predicts that there's going to be a pseudoknot. And we can see here that when you set the threshold value to 0.1, which is 10% probability, then the forms computed by the simple threshold knot and Eterna, which is on the bottom, and the EternaFold ThresKnot seem to be very similar. Finally, there's the conflict shape. And as I said, as it's going down the base pairing list to compute the simple threshold knot, if it finds a pair where at least one of them is already involved in another pairing in the simple threshold knot shape, then it says, oh, let's see that as a major conflict. If it hasn't, if neither, or if only one of those base pairs is previously involved, or both are involved in different ones, then it says, this is a conflict that is highly probable. If it comes across another conflict for one of those base pairs, then it says, well, this is a conflict too, but I'm just trying to find things that I can show easily as a shape, so it throws that away. So in the end, the conflict shape is the most probable conflicting pairs. And both the simple threshold knot and the conflicts are changed by this threshold value that you set here. It walks down the list until it comes to the pairing probability of the threshold. Anything below that, it ignores. The threshold is also used for the base pair threshold display. And that is one of the two grayscale modes that allows you to say, okay, I'm interested in the dotplot data, but I really don't want to go into the weeds. So let's chop it off at a threshold of here, it's 10%. On the top, you're seeing the full dotplot data, and on the bottom, you're seeing that data thresholded at 10%. So altogether, by combining those, you can come up with thousands of different plots, but you can also just use the standard ones. So ArcKnot versus ArcPlot, what's the difference between the two? Well, ArcKnot understands pseudoknots. It understands the square bracket, brace bracket, and angle bracket in shapes, where ArcPlot does not. On the other hand, ArcPlot works with two-state puzzles, and ArcKnot cannot. ArcKnot is an in-game booster and pop-up, and ArcPlot is a standalone web service. ArcKnot has thousands of customizable plots. ArcPlot has a built-in dozen. ArcKnot can pad designs and add unique random barcodes and lab tails, which ArcPlot can't do. Both can detect aptamers, and one of the talks earlier this morning was on switch design and aptamers, and targets. It's got a built-in library of ones that it knows, but that can be adapted. And it can also, thanks to Eli's poking, detect G-quads and I-motifs. And so if you're designing with the latest version of ArcKnot and you notice some red lines and blue lines, those are G-quads and I-motifs that it's detected. With ArcKnot, you can bulk submit designs. ArcKnot has those many extra shapes and the base pairing threshold. Both of them support user-defined target shapes, just in slightly different ways. ArcKnot has more mutation modes, but both can do mutations. So you can use it as a mutation submission widget as well. And ArcKnot has added the color map with shortcut syntax so that it's easy to define a color map, and many more things. So I talked about dirty dot plots. Well, what do I mean by that? Here's an example. Here's the sequence that I used before, and here it is changing the C here to a U here. That one base pair difference created a decidedly different MFE shape. So the minimum free energy shape predicted here has no pairs in common with the minimum free energy shape predicted here. And yet, if you look at these two dot plots of the two different sequences, you can see there are many commonalities in terms of things that are very similar. So you've changed one base, but there's a vastly different result. And this is often the case where, as I showed in the Ensemble, that there are a couple of different possible foldings that are not very far apart. And when you change one base in the sequence, you end up with another ensemble with, once again, a lot of things that are not very far apart. So this kind of situation is something that if we're looking for a stable RNA design, we want to try and avoid. And designing with ArcKnot can help you to avoid that. So what are some examples of using it in practice? Well, here's the OpenKnot pilot, the 50 base or 50 element design by Digital Embrace, which came from the PKB database 386. And she put it in and put some random bases here to fill in. And when we look at it over here, it doesn't look too bad, but there's a little bit of noise over here in this area where those random bases were causing some folding, and also some misfolding up here with the lead-in base, and some over here with the tail. Well, what happens if we look at that in ArcKnot and say, this isn't really part of the pseudoknot that I'm looking at, so why don't I fix that up so that it's not having that problem? And lo and behold, I added in a static stem, which cleared up the dot plot in this region and took away some of the extra over here. And now the score went up by 11. It went up to 83 from 72. And the dot plot looks a whole lot cleaner. Now, I didn't change anything in the pseudoknot itself. I just changed the padding that was at the end by wrapping it up in a static stem. Well, what if we do change part of the pseudoknot? Well, here I added an extra base pair to strengthen the stem and make it 4 versus 4, where before it was 3 and 4. And now we see that the dot plot has become even cleaner and things are much stronger, and the score has gone up 5 more points to 88. So you can use ArcKnot to help in designing. Here's another case with an sequence that Eli picked out of a database somewhere. And it has, once again, a lot of noise in the dot plot. And once again, I cleaned things up. But this time I did actually change the pseudoknot itself rather than just changing some of the free bases. And once again, a cleaner dot plot and a 30-point bump. We're now up to 93. So having a cleaner dot plot can definitely help. Here's a design by UCAD where he had an interesting idea of let's just try repeating the same GACG UCAA multiple times and see how it folds. And lo and behold, the minimum free energy shape looked like, hey, it's got 2 pseudoknots in it. But if you look at the dot plot of that same thing, you see, well, what's far more likely to form is these particular pairings along this axis here, and these other ones that are off axis are not very likely. So why was the MFE shape picked out to be these? I don't know. It's probably a case of the dirty dot plot, and there were a lot of things that were similar energies, and hey, it just picked one. So once again, by using ArcKnot in designing, you could avoid potentially something like this. On the other hand, here's something where Eterna-fold thresh knot picked up a very dirty dot plot, and the possibility of, here it says MFE head and MFE tail, saying that it predicted tail conflicts going on. But if you look in NUPAC, on the other hand, the design forms a completely different structure, has a much cleaner dot plot, and there's no tail conflicts. In fact, it's what the ArcKnot figures is a knot 8 strength, which means that there's at least 8 base pairs here and 8 base pairs here on the 2 sides of the knot. So Eterna-fold thresh knot is not always picking out the best design. Metrics. So I mentioned that there are a couple of different metrics that it can calculate. You can calculate the fraction of A's or the maximum number of A's in a row, same with C's and U's. You can use those for filtering your designs. It can compute the strength of kissing hairpins, which is the number of pairs in the weakest stem of the kissing pseudoknot, or the knot strength, which is the number of pairs in the weakest stem, and several metrics regarding whether there's predicted tail conflicts with the MFE shape or head conflicts, and different metrics in terms of how the various shapes, the K for the simple threshold knot, M for the MFE shape, T for the target shape, and U for the user target shape, computes both a conflict number, which is the highest percent conflict with it, and the U score, which is a measure of how dirty is the dot plot relative to that particular shape. So those metrics, they're somewhat useful. For example, the knot metric, if you look at the open knot pseudoknot 90 results, there's an upward trend of the EternaScore with the predicted Eterna-fold threshold knot metric, but there's also a lot of designs up here which scored very well that Eterna-fold threshold knot did not predict a knot. So it's not 100%. To try and make more clear what I mean by the knot metric, here's an example of a secondary shape structure with a pseudoknot. It's got 4 in this stem and 3 in this stem. And so the knot strength for that would be predicted to be 3, which is the weaker of the 2 stems. And here there's another shape where there's 4 versus 5. There's an extra internal stem, which is not part of the knot, and an extra external 2 pairing that is not part of the knot. The knot strength is 4 because 4 is the lesser of 5 and 4. So as I say, the trend line is an R squared of 0.2, so it's not a very strong trend. There's something going on, but it's not very strong. And that could be in part because Eterna-fold threshold knot is not accurately predicting all the knots. Here's another case of the M score, which is a measure of how dirty is the dot plot relative to the MFE shape. Once again, in Eterna-fold threshold knot versus the EternaScore of those designs. And there is, once again, a very small trend where you can see that there's a slightly higher possibility if the M-score is in this range, and if the M-score is very high, it's very dirty relative to the MFE shape, then it's not likely to score well. So you might use that to prune off somewhere around here, but you wouldn't necessarily say, oh, I want my minimum free energy score to be way down here. If we look at the K-score, which is the same metric with the simple threshold knot and the threshold value set at 10, we can see that the two plots are almost identical. And that's, as I said, the two modes look very similar in terms of the metrics. Like and rank by, in the config mode, there's already a lot of buttons on the control panel. And so for some features, I put them into what I call the config mode, which is where you can specify extra things like, here's what I want my color map to look like. Here's what things I want to look at for pruning. I want MFE head equals 0 means no head conflicts. MFE tail equals 0 is no tail conflicts. Not greater than 2 means the knot scoring should be at least 3. And M-score 1, the 1, by the way, stands for the first state, in case I ever get a two-state mode working here, less than 15 to prune off those excessive ones. And rank by, well, I want to rank these designs by the M-score so that I can look most closely at the ones that have a lower score. Metrics. So in the open pilot round pseudoknot 90, there was no significant correlation seen with the tail conflicts and head conflicts as predicted by Eterna fold threshold knots. So you don't necessarily need to do that, but if you prefer cleaner dot plots, feel free. With mutated designs, cleaning up the dot plot seems to increase the score. With unmutated designs, there are high scoring designs with somewhat dirty dot plots, but MFE score greater than 13 are very seldom successful. Sometimes NUPAC is a better predictor than Eterna fold threshold knot, but it's so very slow to use that for the large scale designs, I don't tend to use it myself. And alas, we haven't found a magic 8-ball yet in terms of using metrics to find the perfect design. Many thanks to all the players who've helped me test this out and given me suggestions. Omei was the one who gave me the initial idea and concepts. And in fact, a few years back, I came and gave an impromptu talk on the first ArcPlot, which kind of usurped his slot on drawing ArcPlots. And Jonathan for his help in API assistance and upgrades. And Eli has been a very patient and exemplary guinea pig for all of this with a lot of suggestions. So I'd like to switch now to demo mode, and I'm definitely open to suggestions as what people would like to see demonstrated, but I have a few things that I'm also willing to show.
So let's start with, there's one question. We'll get that from Thomas. Thomas, do you want to ask it?
Yeah, just briefly, when you switched, I'm assuming that that switch from EFTK to NUPAC, where you showed it cleaned up the dot plot, that NUPAC was with pseudoknot flag enabled?
Yes.
Okay.
Actually, was that done in game?
It was done in game, yeah.
Then it wouldn't have, if you're getting the dot plot, it wouldn't have had pseudoknots enabled.
No, the pseudoknot flag was not enabled for the dot plot, but it was enabled for the folding because the MFE shape predicted had the pseudoknot.
Right. Yep.
Okay, so let me jump in, and once you've favorited one of the ArcKnot tools, I'm going to go ahead and use my latest release, which is 3.62 alpha. It'll show up in your booster list through the lightning menu at the bottom. You start it up and it shows it closed at the bottom. You click over here and now you have a pop-up booster that you can move around to give yourself more or less room to look at both the lab tool and the plot at the same time. As I said before, there are a bunch of different states that are different plots that are built in that you can use, or you can start to play with, oh, I want to see what the user target is for this, and get rid of the dot plot. Oh, there is no user target. Okay, well then let's look at the MFE shape on the top, or look at the thresholded base pair data. Change the threshold from the default down to 0.1. And so now we can see, oh, well, the MFE shape is showing up in blue, but I'm not seeing anything from, oh, not seeing anything from the simple threshold knot for some reason. I wonder why that is. Oh, no simple threshold knot predicted. That's strange. Okay, a bug. Always happens in demo mode. So let's shrink this down a little and we'll go see. I've got the Zika virus genome here. I'm just going to select a little bit from the front end of it. And we'll go in here and open up the notes and stick that in here, close that, and tell the booster that we've got a FASTA file. So now it's parsed it, and we can see that it's created a list of different candidates. So in the Swiss Army knife mode, this is the pseudoknot finder. So it just found a bunch of candidates, and now I click on random, and it's going to go assign those random barcodes and try checking them out and see what do we have. We saw a red line there briefly. That was a G quad that had been detected. Oh, it's seeing a few knots. So now I'm only interested in knots. So I'll do a prune, and we see that, okay, here's one knot that it detected in the Zika virus. It's got a maximum of 4 Cs in a row, and it predicts a knot strength of 5. And that's this inner knot here. There's also another minor knot over here, but it's giving us a strength of 5 because of this knot here. And what's the second one that it found? Oh, this one's a little more complicated. So it's got a knot strength of 5 once again, which is probably this versus this. But it actually looks almost like there's a kissing knot. Maybe not. It didn't detect a kissing knot. It should have. Oh, well. Yeah. You can also, if you have pre-generated some sequences in a spreadsheet, got them from some particular source, you can grab some of those and go, let me clear the notes and paste those in. Close that, and once again, use random to check those. And so it's going through and trying to figure out what's going on there. So here we see there's a blue bar here. That's a feature that Eli recently asked for, which is detecting eye motifs, and it's flagged it up here as there's an eye motif. If we go back, here there is both a G quad in red and an eye motif in blue. And those may affect the folding of the knot. So when we submit those, it will submit, if we submit that through ArcKnot, it will tag those as having G quad and eye motif in the title of the submission. If we wanted to do a mutation on this, we could say, okay, let's focus on this one. I'll make this a little bit bigger. And now, okay, what happens if I, let me just, oops, minimize this for a second and select some base pairs. So what happens if we mutate these 4 bases? Now there are 2 ways we can do that. We could do a mutate n Whoops, first I have to import it. So we imported the bases, and let me try importing again. So you can see here, it's a little hard to see, but I'll expand it up. You can see here there's some blue arcs. That means that these marks have been imported as pairs. And so now if I do a mutate n, it will mutate those 4 bases with 4 possibilities each, which would be a total of 256 possibilities, but many of them wouldn't pair. Or we can do a mutate p, which says, I want you to mutate paired bases as pairing possibilities, and that will do the Watson-Crick and wobble-based pairs, 6 possibilities for each pair. When I do that, now I get 36 possibilities instead of 256. And once again, I can do random, and it will take a look at those and try to find out what different shapes is it predicting. For all of these displays, I'm using Eterna threshold knot because that is definitely much faster than NuPack. If we were doing NuPack, we'd be waiting a minute or so for each of these foldings. And for 36, that would take way too long. And so now, just for fun, we'll do a rank. And so it's put the lowest M score at the bottom. And now we can see, oh, we've definitely changed the shape. And we have some new interesting possibilities. They all still have the G quad and the I motif, because I didn't mutate those pairs. But we can see some of the mutations that I did changed the shape so that it completely lost the knot that it had before. But sometimes it picked up a new knot. So for the current labs, there is some interest in finding out what happens if we try and mutate an existing predicted shape that's predicted to have a pseudoknot. And so you could use ArcKnot to generate multiple mutations and submit those as possible alternatives. Are there any other questions? I see that there's been a lot of activity in chat, but I'm not reading it, so.
Yeah, Reggie was wanting to know, how are you detecting G-quads?
So for G-quads, I do it as a regular expression, which looks for at least 2 Gs in a row, at least 1 to 7 bases, 2 Gs, 1 to 7 bases, 2 Gs, 1 to 7 bases. Eli wanted 2 Gs rather than the standard 3 Gs because he thinks the 2 G cases might be interesting as well. The same for the I quads. It's just using a regular expression to look for patterns.
Well, that was great. Thank you, Jeff.
You're welcome.